Hello, everybody. Thank you so much for joining us on the first Continual AI seminar of 2025. So we are very glad to be starting now with a seminar on task-agnostic continual learning for the open world. And without further ado, let me introduce our first speaker of the day, who is Giuseppe Bravo Roca. Giuseppe is an AI engineer and research specializing in cognitive architectures and continual learning, currently completing his PhD in AI at UPC Barcelona Tech. He develops monitoring agents at the Barcelona Supercomputing Center and has collaborated with organizations like Lenovo and Emory Global Diabetes Research Center. His open source contributions focus on continual learning algorithms and custom agent architectures that help machine learning models overcome critical production challenges, including distribution drift, feature attribution shifts, and model degradation. His research in cognitive architectures and continual learning has been published in top-tier venues and recognized through awards like Intel Lenovo AI Innovations Award. So thank you so much, Giuseppe. And to everybody else, please post your questions in the chat and we will address them at the end of the webinar.
Okay, thank you, Camila. So should I share it now?
Yes, please go ahead and share.
Okay, great, thank you. Okay, well, thank you for the invitation, Camila, and thank you to everyone also for being here. So this is the work that actually I published last year in India. So the name is quite long, but let's focus on these three key words. Okay, task agnostic, task ID inference, and embeddings. Okay, this is a joint work between people from the BSc, the Barcelona Supercomputing Center, the UPC Barcelona Tech, and people from, well, also Intel and Lenovo. So the motivation is how to identify new tasks. Okay, so we worked with the SORA 10 million, which is a data set that works with the driving data set. Okay, so for instance, we have here images regarding several tasks. So for instance, we have cars at daytime, at night, with different scenarios like rainy, weather conditions, clear. Okay, also in on the highway, on the country road, etc. So the idea is how to develop an algorithm that can be good in all the domains. Okay, so that's the idea. So what we did is to just keep two domains, okay, daytime and at night. We included several images for each domain. So for instance, at daytime, we included different, for instance, cars, or for instance, buses, and so on. Okay, so we end up having 6 tasks here. So what we want to solve is the following, is how can we operate at different conditions? Okay, so I was mentioning daytime, at night, weather, or different location, for instance, in different cities. Okay, so also the algorithm should be also learned over time. Okay, preferably with no task boundaries. Okay, and we will just explain that. Because in sometimes we don't have like the boundaries in the task, or we don't have the indicators saying that now you're in the task 2 or in the task 3. Okay, so also we should overcome that. So this is the dataset distribution. We can see here, for instance, in the task 1, which is at daytime, that we see people in some conditions that don't happen in the domain 2. For instance, we have some cyclists here in the time in the task 1, but at night we don't have, for instance, the cyclist. And this happens with different, let's say, modalities in different cities, in the period, or in the location and weather and so on. So there are several drifts. So we have drifts in both labels and also in the input. So I was mentioning, for instance, here, task 1 and task 2. Okay. So this is the problem setting. As we know, we have the easiest case, which is the task in incremental learning, which is given the image and the task, we need the output, for instance. Okay. Here we don't have the task in the domain incremental learning, okay, which is a little bit more complex. In the third scenario, in the class incremental learning, we need both the label and the task. Okay, so as we see, this is the most difficult one. Okay, but what happens is if we can just go from here to this one. So if we help the model to identify X, if we know the task, okay? And also if we know the task, we can also give it. So we are just going from here to this task. And that's the idea of the paper. So this is what happens in the experiment. At time 1, we just learn the model with some images, okay? And let's say we have the daytime, okay? Sometimes happens that we don't want to deal with the raw data, with the raw image. Instead, we can just deal with the embeddings, okay? So what we did is to convert the embeddings, okay? We just clip and also do some clustering to just get the most important points of this just space. So we need that because when new data comes, it can be, for instance, the same task or a different one. So for instance, we have more, in this case, we have a new domain, which is just images at night. We apply the same function here so that we measure if we have a drift here with a simple just algorithm. And we train a classifier, okay, so that we can have the input and yield the task ID. So that if we can do it at inference time, we can get the task 2. If we have this, we can give to the original base model, and we do it just over time. So this is the approach. We just have this embedding step. We just click, but we can use any other model. We get the most important point here. We calculate, well, this is like 2 altogether, the centroid. Then we train a detector, okay? And at the end, we also train a task model, so that just given this point, we use only 10 points, we can give the task ID here. Why is that? Because at inference time, we might have several tasks. So if this image, or if this batch of images don't have drift, we can just get the task ID by using the task model. If we get drift, we can add a new head to the base model. So for instance, in this case, we use the ResNet model. So it started with just one head. But if we just find just new tasks, we can add new heads. So the idea is just to help this model to just overcome new domains by using both the drift model and the task model. So that's mostly like the idea. Okay. And it works in three, let's say, real world scenarios. The classical one, which is the task boundary, which is, for instance, when we already know in the loop that every new batch of task belongs to a certain task. Okay, so or a certain label. So in this case, we got new like good numbers, but not only that. In the no boundary scenario, when we don't have like this, let's say, for loop, we can use the drift model. In this case, we will see if the new batch can see if that domain doesn't belong to the original one. And not only that, also, we also check if what happens if the model also gets, let's say, new batches, but belonging to past domains. In that case, I mean, that's like the more real world, I will say. So in that case, also, this model can, let's say, just learn. And maybe sometimes because we are like repeating. So for instance, this is like the at daytime, this is at night. And if we get this one that can be, or this one that can be at daytime, we can learn some patterns belonging to this that have been learned in the first case. So in that case also it works. So I think I have more time here. So yes. So if you want to check the repo for all this experiment, just go ahead to the repo, also the paper. Some drawbacks that I see is that depending on the pre-trained model, there are some classes that are not trained in the clip, for instance, model. We use clip because that's like the one that have most of the classes. But if we deal, for instance, with medical applications that might have some rare classes, we need to fine tune that foundation models with more particular just labels. So thank you so much.
Wonderful. Thank you so much for that great talk. So the idea of these seminars is also that we have the opportunity to interact. So if somebody would like to unmute themselves and ask a question, please go ahead. You can, of course, also ask questions in the chat and I will relay them. But otherwise, feel free now or at the end of the seminar to raise your hand and you can just ask the question directly. I do have a few questions, but I would say if nobody...
There's
Oh, yeah, please go ahead. Yes, Morgan, please go ahead. Okay, maybe that was an accident. So one question I had was you talked about what would happen if you had like task repetition. So I wanted to ask, in your experiments, did you look at scenarios where you had many repeated tasks and say like 5, 5, 2, 3, 2, and then 5, 5 again, like this sort of pattern where sort of older tasks come by after a while?
Yes, actually, I try with several like combinations. So this is just like one, but actually, yes, I try like 1, 1, 2, 2, 2, 3, 3. So yeah, yes, I try with several one. And actually, I mean, this is just like a one scenario, but in some what I saw, it's some particular scenario, the model behave better than others. So that's maybe because we don't have like the task, the approach that we were comparing to were just like retraining or fine-tuning, because they don't know what to do. But in our case, we can just do more things. So maybe in those cases that we have several repetition, we got not so much gap, because they were like fine-tuning with the same data, and maybe they can just get a boost. But yes, I try with something.
Thanks. Any further questions right now? If not, you still have the chance to post this in the chat and we can address them later. If not, I would say let's thank the speaker again. And
Thank you.
yeah, thank you so much. And let's move on to Megan. So if you would like to present. So Megan Baker is a senior data scientist in the research department at Johns Hopkins University in the physics department. She holds a bachelor in bioinformatics from Bowie State University, a master's in applied and computational mathematics from Johns Hopkins, and will complete a Master of Science in Computer Science in spring 2025. Megan is the supervisor of the AI development section in the artificial intelligence group, where she leads efforts to push the boundaries of AI capabilities. Her work exemplifies a commitment to leveraging cutting-edge AI to address complex, multidisciplinary challenges and has spanned diverse technical domains, including biological signal processing, remote sensing, and the testing and evaluation of lifelong learning systems. So with that, Megan, I will hand it over to you.
Thank you, Camilla. Hi, everybody. As Camilla said, my name is Megan Baker, and I come to you from the Johns Hopkins University Applied Physics Lab. And I'm going to be talking about mine and many other people's work on the DARPA Lifelong Learning Machines program. The paper we specifically submitted is a domain-agnostic characterization of lifelong learning systems, but as Giuseppe pointed out, that's a bit of a mouthful, so we'll stick with L2M. So a little bit about me before I jump in. I was a student athlete in my undergrad, and that will be relevant later. A lot of the analogies we use to talk about lifelong learning involve sports. And I got my master's, and I was doing a lot of biological signal processing. And now I'm getting a for funsies master's, because why not, right? And in my free time, which I don't have a lot of with 2 kids and 3 cats, I like to bother my cats and bake cakes. On L2M in particular, I was the chair of the metrics working group. So L2M was a large DARPA program, and we, were involved in having to design, prototype the metrics, figure out what it meant to demonstrate lifelong learning. And that was a lot of the role that I had. And it resulted in this really wonderful collaborative paper with about 50 program authors, which was a challenge in and of itself. But it was a great experience working with those folks. So let's jump in a little bit and talk about lifelong learning systems. And in particular, I know this seminar series is focused on, kind of the more open world task-agnostic learning. And I think that we can still glean a lot of helpful information and lessons learned from the L2M program, which is the focus of the talk today. So as we know, state-of-the-art machine learning systems are capable of playing games like Go, Breakout, and even StarCraft, and doing quite well, even beating human scores in some particularly focused tasks. And this is extremely impressive. I mean, Go, for example, is a relatively simple game, and it's got an incredibly vast set of possible board configurations. So the fact that we can even do this is remarkable, or even, playing a complicated world domination game like StarCraft is very impressive. Unfortunately, despite those successes and very well-scoped tasks, these systems are more brittle than we expect. And recall that this program started a few years ago, so this is before the foundation model era, which I'll talk about briefly in a little bit. But the point is that even small, seemingly inconsequential changes, or at least for how we interpret these changes, like if you change the color of the bricks in Breakout or varying the size of the paddle, you can end up having a system that completely fails, and that's not great. So unfortunately, despite these advances, these traditional state-of-the-art machine learning systems are really not capable of adapting as fast as the world or an adversary even could change. And this is a real problem. If we know that a system isn't robust to something as simple as a color change, you can imagine that weather variations or the deployment of new vehicles previously never seen, or some disruption, to a previously mapped environment. If that can cause systems to perform poorly, this has serious ramifications for systems where we need reliable, maintained performance. And that's where the DARPA Lifelong Learning Machines program comes in. The goal here was to develop fundamentally new algorithms that will enable this continuous learning, as they've been deployed. And we had the 5, we call them system groups, but these are the lead organizations other than APL. And the APL's role specifically was on the T&E team, so test and evaluation. And our goal was to develop metrics, scenarios, and strategies for how do we characterize and evaluate these systems and make sure that we're seeing progress over the course of the program. And a real challenge is that as a new field with a lot of new challenges, there weren't really accepted standards of metrics or baselines even. We were trying to kind of figure out how to evaluate things that were still even in the art of the possible. So that was a real doozy. To kind of make a tough problem harder for us, the T&E team, each of the 5 system groups, so we had these, I mentioned performer teams, and the lead organizations are pictured along with their primary environments. We had UPenn and AI Habitat, Argonne and L2 Explorer, which is actually an open world exploration environment that APL developed. Teledyne used AirSim, HRL, Carla, and SRI with StarCraft. And these organizations had subcontractors working alongside them, but these were the primary, the leads of these system groups. And you can imagine the challenge involved in making sure that we have made metrics that were applicable across all of these, approaches and in these different environments and domains. So in particular, there were some reinforcement learning focus and some classification approaches across them. So these metrics that we wanted to create, you can think of them as sort of being like meta metrics, and they don't necessarily correspond to good performance in an individual environment, but are rather specific to the system's ability to do lifelong learning over the course of its lifetime. So, we were dealing with a lot of really messy things in terms of the variability in the environments. We needed these metametrics, and part of the challenge involved here is that a lifelong learner or lifelong learning system, it's not a single model. It's often a system of AI components that each are kind of their own field of research, just because of the challenge of creating a system capable of doing lifelong learning. So, for example, you might have memory consolidation modules or replay or attention, and all of those things, you could find lots of current state-of-the-art work in those areas, and bringing them all together and developing this new system, and especially if you're trying to assess it, raises a lot of interesting questions and trade-offs. Like, what do we do when a component is added? How do we make a fair comparison to the previous performance versus the new performance? And how do we measure progress when we don't have baselines in this field that's very nascent? So our approach to doing this evaluation was to kind of have 3 main, focuses, I suppose. First, we needed to define success. What does it mean to do lifelong learning? What are the conditions that would satisfy something that we might refer to as a lifelong learning system or a lifelong learner? Two, we needed to identify key parameters for evaluation scenarios. That, the set of all possible scenarios is very large. And so, what are the key drivers for performance, or what do we imagine those might be, and how can we make sure to assess the systems along those axes? And number three, we needed to specify these metrics, these meta metrics, to identify and assess these trade-offs that may be happening when we introduce new components, or where we're aiming for increased performance in one particular domain. So just a note about some terminology. I was reviewing some of this content, and I realized how often, or maybe not often, depending on how you think of it, we were using the words agent, and that means a lot different, I think, now versus what it did back in at the beginning of the program. Independent of your feelings about foundation models and the kind of new era that we're in AI research, foundation models haven't solved continual learning or lifelong learning. And while fine-tuned LLMs may be zero-shot learners, we're not actually sure what's happening with in-context learning. There's a lot of muddying of the waters. So we really do still need these rigorous measures of performance across multiple tasks. And I think in particular, transfer metrics are important, specific to foundation models more so than they were to the lifelong learning systems that we were evaluating in L2M. And we didn't consider in-context learning or anything like that, because this kind of happened right at the end of our the work on DARPA L2M. And then just kind of as an example of how we might apply kind of this same framework and thinking to this in-context learning idea, or the zero shot, is if we're in the same session and LLM is prompted to do task 1 then task 2, how might it perform differently if it's just prompted to do task 2, or if we fine tune it to do task 2 or task 1? And so there's lots of variables at play here that affect performance, and I think there's still some lessons to be learned, or to draw from L2M. So let's talk first about the conditions of lifelong learning. I mentioned I like to use sports examples. This wasn't just my bias from the program. Lots of people think about sports as a way to think about different tasks. And I think that's because we think of tasks as being similar, or sports being similar to each other, based on our semantic understanding of either the rules or the mechanics of the sport. So for example, you might think that tennis is very similar to badminton because they both use rackets, and you would expect a lifelong learning system to be able to, or a lifelong learning Serena, to be able to be very good at badminton, given that she's an excellent tennis player. But going with his example of a lifelong learning Serena, if you will, we expect her to be, excellent across various variants of tennis, right? Versus the court being clay or grass or hard court, or certainly in different weather conditions. But really, none of that changes tennis. It's still tennis, but there's these variants, and we need her to adapt to them and, perform well at them in order to be a lifelong learner. And I mentioned transfer. Side note, it is very difficult to find a picture of Serena Williams doing anything other than playing tennis. So really had to scour the internet for these. But you expect that somebody who's very good at tennis is also going to excel at badminton. And you would hope that you would also potentially get improvement in tennis based on playing badminton, because we think, or we have hypotheses that suggest that there might be some overlap in the skills required to do both. And lastly, we want this lifelong learning system to sustainably, efficiently perform for a long period of time. And this is really more, the three of these conditions are more than just a sequence of zero-shot experiences. We want a system to live its life, if you will, while experiencing and learning and adapting, leveraging information experience it gets as it goes. So the second thing we wanted to do was think about evaluation scenarios and how we can, assess these lifelong learning systems, understanding that there's a lot of variables that impact performance. We can think of curriculum learning as something that's very extremely curated and can improve the performances of a system. But then if you do that, you may not be robust to randomized sequences at the other end of the extreme. So we wanted to have consistent and thorough evaluation. So we use these two primary forms of evaluation scenarios where all of the experience on a specific task, so think tennis, is all happening all at once versus spreading it out throughout the lifetime. And this lifetime is all of the sequences of learning, different tasks or evaluation after it's been previously, has this pre-training. So again, to kind of just emphasize here, we have a system that's gotten to this ready to deploy state after some initial training. It experiences tasks and it learns from them, hopefully, while there may be some dips in performance overall, the course of the entire lifetime, we want, expect, and hope that it will continue to improve performance. And some of the most robust characterizations of these systems come when we compare a system to a single task expert. So that's pictured in purple here, showing that if Serena Williams never ever did anything else in her whole life except play tennis, that's what her performance notionally might look like. And those make for some good comparisons for our program. So, one of the most important points, I think, in when we were considering these metrics is that lifelong learning involves multi-optimization, right? Like, not all things can be optimal when we make these systems that are so complicated. And so we have to characterize the system's performances, both their strengths and the weaknesses, via multiple measures. And I can't stress enough how important that is. And like, there's, obviously folks probably on this call who are working on things like overcoming catastrophic forgetting. But if that's the only thing you ever do, then you may be more vulnerable to other areas where your system isn't as performant. So we've open sourced our metrics, which we'd love for you to take a look at. But let me just really quickly run through some of the metrics and what we were hoping they would do. So performance maintenance compares the performance at the end of a previously learned task to the beginning of the second one, essentially saying like, hey, don't forget stuff as you're going. And this is one of our best measures of to mitigate catastrophic forgetting. And I'll just keep going through these pretty quickly here because I don't want to use up all the time. Forward transfer, so the idea that for this particular scenario, learning tennis makes you better at learning badminton for the first time. The thing about adding transfer metrics is you have to introduce these evaluation blocks where you have no weight updates happening during those things. So that does kind of create some constraints on the amount of things that you can do, the number of inferences you can make. So we only assess these for the first instance of task pairs and basically computed what's the gain you get by learning task 1 first before you see task 2. Backward transfer doesn't have that constraint because we didn't consider that to be an important part of assessing backward transfer. So this one was easier to implement because easier to create robust statistics for because you could do it many times throughout the lifetime, but you still have to have these evaluation blocks if you're going to, in my opinion, make a fair assessment of backward transfer. And then relative performance is one of the metrics where we compared performance to the single task expert. And we left this to be very general kind of on purpose, but the idea here is just, hey, compared to a single task expert, if you line up all the experiences specifically in badminton that you have, how does your performance compare to this single task expert? And do you get any gains, hopefully, from doing your lifelong learning approaches? Similarly, sample efficiency does the same thing where it stitches together all these experiences, but it computes 2 specific things. First is the saturation value. So overall, if you max out at a certain value, what is that? And how does that compare to a single task expert? And then also, how long does it take you to get there? Are you more efficient by doing this lifelong learning approach? Hopefully, if you are leveraging transfer, you are, but that wasn't always the case. So in general, we had these metrics that, kind of assess the ability to do things that we thought were these conditions of lifelong learning. And if you are an astute observer, you might notice there are 6 metrics here, and I only talked about 5. Performance recovery was a really challenging one because of the difficulties in assessing task similarity, which again, another open field of research. And we made some choices that made it really difficult to assess for performance recovery. But overall, what we focused on doing was making thresholds where we could say, hey, this system is or isn't demonstrating lifelong learning if these metrics were above or below this number. And I think that was really helpful to have a clear goal to be like, hey, the minimum viable product here is not forgetting. So let's not forget. And if you can gain past that, then even better. So, I've mentioned trade-offs a couple times, and, stability plasticity is the one most often talked about in this domain. And we certainly found evidence of the stability plasticity dilemma here in the system group case studies that we had. But I think optimal performance and computational cost is, it's never been more clear to me, certainly now, with new models coming out that are performant but smaller than, the GPTs, is it possible to optimize performance and minimize computational cost? We didn't explore that for the program just because of the limitations of kind of having everybody run in the same environments. That's a real challenge. But we did see evidence of sample efficient versus robust learning. So wanting to see a system prioritize a fast performance gain, even if it may not be as robust in the to-task variation. So in terms of our lessons learned here, I mentioned the task similarity bit was a real challenge. This was basically assumption 2. It's like, if we make the assumption that if you drop in performance, you can bounce back, that might not always hold, right? Like there are tasks that where learning conflicts with other skills, and our assessment of whether a task is similar in our experience is based on semantics, that a system may not have those same drivers. And so we found there's a real need for assessing task similarity so that we can understand what's the maximum performance you can expect if you learn a sequence of tasks. Because just like assumption 1 states here, like we assumed that learning a particular sequence of tasks and maintaining performance is possible, but that might not always be the case. So, I don't want to belabor this too much here, but we have some recommendations that came out of this program. And I think that the comparing to a single task expert for these particular systems is very important. It was some of our most interpretable and robust metrics that had kind of incorporated overlapping concepts. So like that's a thing that we didn't avoid. We wanted to have multiple measures, even if they just kind of took a slightly different look at the problem. And I think that was a really good outcome of what we did. And, as the systems to try and solve, today's problems get more and more complicated, that's only going to increase the difficulty of evaluating them. And using a consistent suite of metrics, or by using a consistent suite of metrics, we can really enable tracking of progress in a field where baselines are hard to come by, since task sequences are already hard enough. We'd love to extend this work, and we'd love to work with you to do that. We've open sourced some of the tools we have available. I mentioned L2 Explorer is our open world exploration framework. We've got Meta Arcade, which allows you to do lots of test sequences with some inherent similarity measures built in. We've got other ways to help with evaluating lifelong learning agents, including metrics and other trade-off measures. And we'd love to add metrics to this or collaborate to invent the future with you all. And before I wrap up, I just wanted to thank all of the co-authors on this work. I mentioned it's about 50 people. It was a great time working with you all, and I'm very pleased with what we were able to accomplish on the program. And certainly, I'm hopeful to see that our work can continue into the future. So that's all I've got.
Well, thank you so much, Megan, for that great presentation. Does anybody have questions? You can ask this in the chat, or you can also raise your hand, and you can just raise your hands and unmute yourself.
I have one. Can you hear me?
Yes.
Yep, I can hear you.
Okay. So it's not completely clear to me what is an evaluation block in your figure, because are you thinking of a deployed system? Because it looks like the agent is stopping to do the evaluation. So I'm thinking like there is a single process, you stop, you have some kind of internal test set.
Yeah, you're right that the evaluation block doesn't really extend to deployed systems, right? Like we don't want to have to take our systems offline to be able to evaluate them. So this is definitely still in the low TRL. Like we're trying to prove out that this is happening. And so the evaluation blocks are where no learning is happening was kind of our explicit, and it's a little specific to the evaluation criteria that we had for the program, but I think it's still an important measure that we can definitely, if you just checkpoint a model or something, you can evaluate at that point. That would be a potential alternative to kind of taking it offline. Did that answer your question?
Yeah, it makes sense. Okay, I have another question actually.
Sure.
So one of the issues that I have with the continual learning literature is the use of the forgetting metrics. Like, when you compute the difference between the accuracy at some time and then the accuracy at t plus n. Because in my experience, people don't really know, many people don't really know how to interpret the metric. Like they say, oh, you have less forgetting, and then that means that the model is better. But actually, if you learn less in the first step, then you also have less forgetting. So I'm wondering if you have some other examples of this kind of unintuitive stuff that happens.
Yeah, so I mean, the comparisons to the single task experts are another example of that. We didn't, and so like I said, some of the lessons learned we have were specific to the evaluation of the program, where you have to demonstrate progress in order to keep getting money, right? So like some of that is a little artificial, but we did focus a lot on trying to make sure that the metrics weren't like easily gameable, right? Like on the one hand, if a metric is a target, it ceases to become a good measure, right? Like it's a good hard swallow. But on the other hand, so you could easily, sorry to page through here, but you could easily make a poor single task expert, right? And then you've got great performance compared to the poor one. And we just kind of left that up to the specific system groups decisions for what those single task experts were. But there were some, I have one of the lessons learned that's about ratios in particular. So since some of the metrics involved ratios, that did kind of throw things off a little bit. Like if you didn't ever saturate a task, that made things difficult to compute comparisons for.
Yeah. Okay, I actually have another question.
Sure.
So the single task expert,
Yep.
What is the single task expert, right? Because the performance depends on how big your model is, how much computation do you give to it.
Yeah.
So
I believe, and I have to double check, but I believe for the program, what we requested the system groups do is essentially use the system that they designed to be the lifelong learner and just only ever have it learn on the first task. So for this one, it's like the same system that really would do this task sequences learned just tennis. Now, is that the best comparison? No, of course not, because that's something that's specifically tuned to excel at one task. It probably makes the ceiling of performance a little artificially high, which was, lots of these kinds of considerations were the source of many meetings over a long time. But in order to like assess progress, that was the main point of the metrics, right? It wasn't necessarily to make the claims that like, this is the best system ever. And again, that kind of goes to like the metametrics concept, right? Like this is just designed to say, are you demonstrating lifelong learning independent of your individual performance in a specific task?
yeah, that makes a lot of sense. Thank you.
Yeah, no problem.
Great. Any other questions? So I have a question on, you mentioned that I completely agree with you that sort of these advanced or foundation models creates a very big question in continual learning, which is, okay, how do we evaluate it? Because it has always been complex to evaluate continual learning because you want to sort of get a good trade-off between plasticity and rigidity, and you want to don't forget, but still be able to acquire new knowledge. And now we have the additional scenario that we have models with many different tasks, some of them self-supervised, as well as many different domains of data. So it seems like the evaluation process is now a lot more complicated, right? Like, what do you think is a good way to figure out what to evaluate?
Yeah, that's a great question. So I think that in some ways, the evaluation process kind of got on the lifelong learning machines level, if you will, right? Like suddenly we have sequences and various points in the system where we are learning, but only a little bit, or, and this even just like with as vanilla as you get foundation models, right? Like you have this base training, and then you have this second step where depending on what you want to deploy the model to do, you might train in a different way. And then you have got the zero shot experiences. And it's like, there's lots of then essentially sequences of learning that we need to evaluate. And so in some ways it's the same paradigm as what we're doing in terms of evaluating a system over its whole lifetime. It's just the idea of what a lifetime is changes a bit. And it's funny because as I was looking through this content again, I was looking to see, when I was initially presenting some of this to, to internally, basically people that weren't on the program at APL, the idea of this like pre-training in red was like, what is that? What is happening there? And now we have a pretty easy understanding of that because we can relate it to foundation models and the pre-training that they do, that they're acquiring general knowledge before they're acquiring specific knowledge. And the acquiring specific knowledge is essentially what this lifetime is representing. So in some ways, I think it does make evaluation more difficult, and it emphasizes our need to evaluate over sequences, which is hard computationally, right? Like it's hard to do that.
Exactly. Yeah. So yeah, I think this is just an amazing overview of all of the aspects to evaluate. So these slides are really lovely.
Thank you.
I think Julio may have a question because you turned on your camera.
Yes. Thanks both for the presentation. They're really interesting. I have a question that maybe touch a little bit of both of the presentations. My question is when to learn, because you mentioned, Megan, this idea of using pre-trained models and the idea of how specialized and generalized these models can be. But the question is, if we have a new task, like in an open world situation, if we have a new task and we have some performance, do we need to learn something? Can we know if we learn something that's going to be better for the future, like for better generalization, or is it like, no, if we specialize, or maybe we forget these generalization things and can be harmful for the model?
Yeah, I think that, I mean, it's the worst answer to give, but I think the most reasonable one is that it depends, right? It depends on what your requirements are. And that's like the whole point of the trade-offs part is like, yeah, maybe you need to maintain performance on this specific task and you never wanted to change unless you have explicit new information about what that might be. And like recognizing stop signs for autonomous cars is a great example of that, right? Like I don't want people to update recognizing stop signs unless like globally we change what a stop sign looks like. So, there are some things that need to be rigid. And it's not necessarily reasonable to assume or want a system that can have both very rigidly held beliefs, if you will, or performance alongside things that need to evolve, like new cars or new paint colors or, different weather conditions. So in my opinion, the AI research answer is different than the practical considerations for deployment answer. That's like I said, that's not a satisfying answer, I think, for many people. But I think it's the real one, is that operational constraints have to determine what you decide to employ and how you evaluate performance.
Yeah, exactly. I mean, just to add just one thing, as you were mentioning, Megan, sometimes when we just find some drift or some metrics, maybe that we see that, okay, maybe we just retrain, fine tune, or just change like the task, but some business metrics just don't follow that. So
Right.
it just depends on the data. So that happens when you just have your model in a cluster. For instance, we work with clusters, and there's several metrics, but we somehow need to find just like a global metric that say that, okay, we should just forget, we just learn new things. So what is the idea? So at the end, like the last voice or the last decision it's just made by the client, I think, or the customers. So they just say, okay, maybe that's the good one. I mean, you should just forget, because now the scenario is just changing. So we don't need just to keep like the old data. So that for me is better just the other. So yeah.
Thanks.
Okay,
Both.
another question. Oh, sorry, go ahead.
And that was it. Thanks.
I have another question also for both presenters on the topic today is task-agnostic continual learning. So that often refers to when we have like very slight shifts in the data distribution and possibly even like multiple shifts going on on tandem, which are related to multiple aspects. And so many of the continual learning methods that we know assume that we have like these clear code differences between tasks. So do you think there has to be like a separation of the process of, okay, we identify that there is a distribution shift? Or do you think it just makes more sense to design methods that can natively deal with these sort of slight changes in domain?
Well, maybe I can start. So yes, as you say, I mean, it's like in most of the paper, you will just receive a batch of examples just belonging to one task. But what happens if you just combine like 1,000 examples with 10 tasks? I mean, just batches of, let's say, 10 items, 20 items belonging to the task 2. So that's difficult because most of the for loops in the algorithm, for instance, just make you or just allows you to deal with just one batch belonging to one task. So in that scenario, what I will say is that the model should have just one way to detect this difference. If not, I mean, it won't be so real, I think. I mean, it will be like more into the academia than in the real world. So that model should learn that. I don't know if that should be end-to-end. I mean, if the model should learn to detect new tasks, or if we need to put another model so that it just combine just more or less. So well.
Yeah, definitely having like a hierarchical system is a way to approach that problem. I mean, I think that a lot of times in these circumstances, you know, we know what the distinctions between these things are, and we just maybe don't provide that information to the model, right? And that's a different thing than not truly being able to distinguish between what classes or tasks there might be. On the other hand, like lots of our versions of what a task or a class is are very artificial, right? So there is a lot of overlap. So there's like a lot of things to consider, I think, when you're deciding which version of approach you want to handle. And I don't know that some of the metrics that we've developed are kind of robust to those differences, and some of them, because we are comparing in-class performance across a lifetime, would maybe be a little challenging to adapt to a truly task-agnostic approach. But like I said, I don't know that there's all that many examples of like a truly task-agnostic learning, within the context of where we're operating in for lifelong learning. Otherwise, how do you assess performance, right?
That's a good point. How do you assess performance? Because should you keep like many different types of subset of like test sets to measure performance on, which I mean it is a possibility.
Yeah.
I think it's always connected this with, and you talked a lot about performance monitoring, Megan, as well. How do we decide, okay, if our continual learning method is performing well? How do we say, do we prefer to perform best on previous data or adapt to new tasks? Such as, I guess it depends on a case-by-case basis. So potentially you would say for real-world scenarios, you would need to decide for your setting, okay, what are the test sets that you use, how you monitor these changes, etc.
Sure, yeah. I think that's the most reasonable answer in terms of actually getting something good out of the model you've created.
Yeah.
I mean, if we think about human behavior and how humans acquire and advance their own knowledge, it's not certainly one task at a time. There's lots of repetition, but there's also lots of performance drops that eventually bounce back, right? Like a child's vocabulary expands and then it compresses as they've learned new things, or they have these, they walk and then they learn how to run and they suddenly can't walk anymore. They can only run, like there's lots of things that we can point to in terms of human development that I think can inform, but shouldn't necessarily constrain the way we think about evaluating machines.
Yeah, makes sense. Okay, we have 5 more minutes. Any other questions in the chat, or maybe is there any topic, Giuseppe, Megan, that you would like to discuss?
From my side, okay, I think.
Yeah, it was great to be able to share and hear from Giuseppe too.
Yeah. Oh, thank you so much to both of you. We will upload this recording to our YouTube channel, where you can find a lot of material, like a lot of past seminars, a lot of continual learning courses, etc. And basically now we have restarted the seminar series for 2025. So we will always have this at the same time on the first Thursday of the month. So with that, thank you everybody for joining. This has been a lot of fun, and I hope you have a great day, evening, etc.
Thank you so much, guys.
Thanks very much.
Thank you so much.
Cheers.
Bye bye.
Bye bye.